Hello everyone, and welcome to our presentation on Gaussian label distribution learning for spherical image object detection. My name is Hang Shu, and I'm part of a team of researchers from Hangzhou Dianzi University and the Institute of Computing Technology at the Chinese Academy of Sciences. In this video, we'll be discussing our recent paper on object detection in spherical images, which was accepted at CVPR 2023. So without further ado, let's get started. First of all, we'll start by giving you an overview of the problem we're trying to solve and the main idea of our approach. In our paper, we aim to overcoming intrinsic flaws of LN norm loss for object objection on spherical images. That is independent optimization and inconsistency with IOU metric. We convert spherical boxes into Gaussian distribution on tangent plane, and design sample selection strategy GLDL ATSS and joint optimization regression loss GLDL loss based on distribution distance GLDL, which is more consistent with IOU. With the help of this series of methods, we circumvent the above flaws and significantly improve the detection performance on mainstream datasets. If you are interested in learning more about how we tackled this challenging problem and achieved these results, then keep watching. Before we get into our solution, let's first review some of background and prerequisite knowledge. They will help you better understand our approach. For the demand of comprehensive environment perception in emerging applications, object detection can be naturally extended from planar images to panoramic images, because the latter have the whole 360-degree view with richer information in a compact form. Unlike planar images, panoramic images usually take the sphere as the imaging surface and are stored in the ERP format based on polar coordinates. To tightly enclose objects on spherical images, mainstream method usually replace planar rectangular boxes with spherical rectangular boxes, which is also known as the bounding field of view, BFOV, where p theta phi is the tangent point of the sphere and rectangular tangent plane, while alpha and beta are the horizontal and vertical fields of view of the spherical bounding box. Gamma is rotated angle of the box. Many existing detectors use L1 norms loss for regression of spherical bounding boxes, but L1 loss optimizes box parameters independently and it is inconsistent with metric. Different from planar boxes, moving spherical boxes without L1 change maybe causes sharp IOU change, which exacerbates the above-mentioned problem. To address these problems, we propose a simple but effective solution based on Gaussian label distribution learning. Specifically, we convert spherical bounding boxes into Gaussian distributions and design a dynamic sample selection strategy GLDL ATSS and joint optimization regression loss GLDL loss in an alignment manner on the basis of KL divergence. Having discussed the overall approach, let's now delve into the finer details of our method and explore how it works. Let's start with the simplest case. When the object in the polar region, its tangent plane is pi 0. It can be converted into a Gaussian distribution n, mu 0, sigma 0. Moreover, when the object in other region, we can establish a new coordinate system based on its tangent plane pi I. Then, Gaussian distributions n, mu I sigma I can be constructed based x, I, y, I, z, I. Finally, we can utilize KL divergence of predicted and target distribution to mean the similarity of boxes, and sample selection function and loss function can be constructed furthermore. Now that we have covered the technical aspects of our approach, let's move on to the experimental results and see how our method performs in practice. Firstly, we make a comparison between our proposed GLDL and spherical IOU. On the one hand, GLDL has significantly greater consistency with SVU than L1 norm. On the other hand, GLDL has significantly greater scale invariance than SVU. To further validate the effectiveness of our approach, we conducted some ablation experiments to examine the impact of key design details. Firstly, We test detection performance under different hyperparameters tau and c. And results show that our method is robust to these hyperparameters. Secondly, we analyze the normalized function for smooth L1 loss. And results show that improvement does not come from normalized function itself. Thirdly, we test different combination between sample selection strategy and regression loss. And results show that our proposed GLDL ATSS and GLDL loss can cooperate with each other to improve the detection performance. Now, let's move on to the classic datasets and detectors that we used for our experiments. Obviously, GLDL ATSS and GLDL loss improve various detectors on two mainstream datasets. Finally, to provide a more intuitive understanding of our results, we'll show you some visual comparisons between our method and classic approaches on several mainstream datasets. As you can see, GLDL ATSS and GLDL loss help detector to get more precise predicted results. That concludes our presentation on Gaussian label distribution learning for spherical image object detection. We hope you found it informative and engaging. Once again, I'm Hang Shu, and on behalf of our team, I'd like to thank you for watching. If you have any questions or comments, please feel free to reach out to us via email or social media. Thank you, and have a great day.